Ready? Go ahead.
Hey, Jordan.
Okay, so we're going to go over our very last section of notes, volumes by cylindrical shells. Now I'm going to be using my hands to describe things, Jordan, so just imagine me. I'm wearing corduroys and okay, and it's a glasses day. All right. So some solids cannot be done with discs and washers. Have you run into one of these? No, because all the shells homework is at the end. Okay, so some volumes cannot be done with discs and washers, and this happens when the area in which you're rotating, okay, is a distinct either top minus bottom or right minus left, and your cross section of that area, like let's say you had to do a top minus bottom, okay, that cross section has to be vertical then, right, if you have a top minus bottom area. Then if you were to revolve that around the y-axis or any vertical line, then the cross section of the area is parallel to the line of rotation. And if you imagine a line revolving around a parallel line, the shape that it leaves behind is not a washer or a disc anymore. Perpendicular cross sections leave behind washers and discs, but parallel cross sections leave behind toilet paper rolls when you rotate them. Okay, so now I'm going to draw this out. Hold on, I have to pause. Okay, so for example, let's think of somebody who has a distinct top minus bottom. Maybe an upside down parabola and the x-axis. I'm talking about this shaded area here. I cannot do right minus left there, right? Because the right side and the left side, they're both the same curve. So this is definitely a top minus bottom when you look at a cross section. All right, let's say I want you to rotate that around the vertical line, x equals, I don't know, 4, something larger. So like if this is y equals 4 minus x squared, then I intersect at 2 and negative 2. And so when I rotate a cross section around this line of rotation, do you see the toilet paper roll that it's leaving behind? It's also called a cylindrical shell. The cylindrical shell, rather than a washer. A washer is what you would have gotten if you rotated around the line y equals negative 4, because then your top minus bottom is perpendicular to the axis of rotation, and the trace that it leaves behind is a thin washer, whereas the trace that you leave behind when your cross section is parallel to your axis of rotation is a cylindrical shell. Okay? Now, cylindrical shells are not on the AP test, but you can use them. I have graded questions in which people use cylindrical shells. I will tell you this, though. It was hard to get partial credit with cylindrical shells. Like it was like either you got it all the way right and you got full credit, or you messed up one thing and you didn't get any partial credit. So we're going to learn cylindrical shells because it's a good thing to learn and it will help you in Calc 2. But when we go to the AP review, I'm going to really encourage all washers and discs based on my experience grading. But shells are right. They're a good thing and they're right. Yeah, Perry.
How do you know, like, when you have a washer and you have a full disc? Like, I have a picture in there.
Okay, so the most important thing, the very most important thing in all volumes of revolution is to look at the area you're rotating, the blue shaded area up there. And if you look at that blue shaded area and you say, is this top minus bottom or right minus left, it's going to help you with a lot of things. Okay, sometimes it can be either. If it can be either, you can always do washers.
Sorry, like sometimes I think I have to move it to like the x cube function and one that always with like another one, like so that connects top minus bottom to the
That's right. This can be top minus bottom or right minus left.
There's one like Like we didn't have to move it all to the right minus left, we moved it to the y.
Okay, sure. I don't remember, but yes. Yeah. Yeah, so you can do top minus bottom or right minus left in this example. By the way, there's going to be a test question in which you can do either one, okay? And I ask you to do both. Does that make sense? So you have to do both. Okay, so then you can always just choose on this. But then we teach you cylindrical shells because sometimes you really can't choose. You really are bounded by that area of top minus bottom. And then when you rotate around this vertical line, it doesn't, a vertical cross section rotated around a vertical line does not leave a washer. So you have to learn cylindrical shells. Okay. All right, so let's do this example. I'm going to, well, before we do that, did I review? Yeah, here we go. What's the surface area of, okay, so let's talk about what happens when we do this. So we have an area that's rotated. I'm just going to stick to this original example that I had for a second. When we rotated that, okay, so here's one thing, one cross section that you get. When you do an inner one, you get a smaller toilet paper roll. And the biggest one is going to be at that vertex, right? And so these are like nesting dolls, right? There's like the Russian nesting dolls. Have you ever seen those? Where you open it up, oh, it's the same thing inside, but just smaller. That's exactly what happens here. And so by the way, this is a bundt right here. This is a bundt cake, right? It's a bundt cake. When you rotate this parabola around this line, you get a bundt cake. So how do I figure out what my cross-section of the volume is? Well, every single cross-sectional volume slice, imagine a strange slicer that slices only in circles or something. And so you get, but they're all cylindrical shells, right? And so if you look at this cylinder, okay, it's hollow, okay, it's hollow. So how much volume does it have? Well, it doesn't really have volume, right? A hollow cylinder that has surface area. So the surface area of it is how much? Circumference times height. It would be area times height if it were filled. But we don't, if you think about the cross, now I'm doing cross sections different, but if you think about this, this is just a bunch of different rings added up together. And the rings have, so the surface area is 2 pi r, the circumference, times h, the height. And so what about volume? Well, we think about this cardboard toilet paper roll or paper towel roll as having a really thin thickness to it, right? It has a thickness to it. Now, the thickness is a dr because if your radius goes from the center out, then there's a certain amount of error there because of the thickness of the cardboard. And so the volume is 2 pi r h dr. Now R is going to be x or y based on whether you have top minus bottom or right minus left. Okay. So in this case, we have top minus bottom, right? That's area. That's the volume of a cylinder. But the surface area of a cylinder, the lateral surface area is 2 pi r h. Are we doing surface area? So that's going to be equal. We are, and this is actually dV equals, because I'm talking about the volume of a toilet paper roll, where just that cardboard, inner roll, how much volume does it have? Okay, so you just multiply by the thickness, and that's the third dimension to get you the volume. Okay. So the same rules apply. Top minus bottom means you have functions of x, and right minus left means you have functions of y. What's different here is that it's not according to the axis of rotation. Okay? So usually if you went around a horizontal line, it was always dx, and if you went around a vertical line, it was dy. That switches in the case of cylindrical shells. That's why I never told you that, because I don't want you to think that. But what stays consistent throughout all of these problems is the area you're rotating. If the area where you're rotating is top minus bottom, then you have functions of x, and the integral has x's in it. If the area you're rotating is right minus left, then you have functions of y, and the integral has the letter y in it. Okay, so let's just do some examples. Looks like I'm blabbering on. Okay, let's see here. This first one, x equals 2y cubed minus y to the fourth. That's not an easy one to graph, right? But we're going to sketch it anyway. Let's see here. What if y is 0? Then x is 0, right? Let's find the other x, y intercepts. So I'm going to set 2y cubed minus y to the fourth equal to 0, a y to the third, which factor out. And so it looks like my other intercept is that y equals 2. Y equals 0 and y equals 2. Let's just plug in y equals 1, since that's somewhere in the middle. If y equals 1, then x equals 1. Okay. I don't know what this looks like, but actually I kind of do. But it looks something like this. I know that the only intercepts of the y-axis are 0 and 2, right? Because I solved that. This is it. Doesn't cross any other time. And I know that in the middle, I get to the right somewhere. So I know I should have an area like this. Orange. Okay. Do you have right minus left or top minus bottom? Your answer will have what letter in it? Y. You know that. And I haven't done any volume of revolution at all, have I? I don't even know if this is a disc or a washer or a shell. I just know that this is right minus left. And so if I have right minus left, the answer has y. Okay? That will always be true, whether it's shells or washers or whatever. Okay, what are we rotating around? The x-axis, yes? Okay. So, oh, this is a different bundt cake, vertical. And it doesn't have a very good hole in the middle. It kind of comes together. So I have a cross section. I have to do a right minus left. So I take the right minus the left, and I rotate that piece around the x-axis, and the trace that it leaves is a toilet paper roll. So what I'm doing is, see my orange area? I'm taking a slice of it. And then I'm taking that slice and I'm pretending like it's wet paint. We have 3D printers now, right? So I'm pretending this is a 3D printer, and I'm leaving a trace behind of all of that printer, whatever stuff that it makes. And then what it leaves is that toilet paper roll, right? Okay. And so now I know what kind of area I have to work out. I have to work out the surface area of a cylindrical shell, because that's what my cross section of the volume is. Now when I take a cross section of the volume, a knife doesn't work to find it. I can't cut it. Instead, it's cutting like with a cookie cutter. Yes, Barry. Like 0 in that? The orange area? I did. I rotated all of it, but I'm taking, so one of the things that we do is we rotate the entire area. But when we set up our integral, we think of it as one section at a time. It's too much to think of it all at once. And so that's why I always do a cross-sectional slice of the area, and then I rotate just that cross-sectional slice. really what happens, Perry, is every single cross-sectional slice gets rotated. And so there are infinitely many cylindrical shells here, all nested inside of each other. I'm just looking at a typical one that I'm not labeling as specifically the vertex one. I mean, that's where I drew my. Are we good? This is called the representative cross-section. What's hard is that our representative cross-section in cylindrical shells is a three-dimensional shape, whereas in washers and in discs, there's really a two-dimensional shape. It's really three-dimensional because you multiply by the thickness, but it definitely you see the three dimensions in the toilet paper roll cylindrical shells. Okay, so I have a cylindrical shell. I'm going to write that down. Cylindrical shell. So that means I need to say that my area of the cylindrical shell is 2 pi r h. This is why shells are hard, because the area formula for its surface, the surface area formula, requires 2 inputs. It requires 2 inputs. And all of the other ones that we did, the discs and the washers, and even the cross sections where they were triangles or whatever, we figured out how to only put in 1 input, right? Oh, r is, x squared minus 4, or r is 2x, and then you just replace the r with what it was in the formula. Well, this formula requires 2 inputs. So I have to figure out r and I have to figure out h. Okay, I'm going to do that in blue here. Here's my representative cylindrical shell. Okay, so if you look at this representative cylindrical shell, my h is that horizontal line here, right? That's h. I need the center. That's an h. And the radius, again, the radius goes from the axis of rotation out to that cross section. Now, if you look at the area that you rotated, right? The area that you rotated, does that count for h or r? It counts for h, right? H is inside, is your right minus left. And that will always happen in shells, is that h is the right minus left if you have right minus left, or it'll be the top minus bottom if you have an integral with x's. Now, r is sort of a dummy variable. He is just going to be the letter y here. And this is y, okay? See this point? This blue point, and maybe I need to highlight it. Let me make it yellow. See this point? Okay, this point has 2 coordinates to it, so you could think of it in 2 different ways. One is this yellow point, it's on this curve, right? And so if I know what y is, if I call y y, see how x is, we're going to have a fire drill, I think. Maybe not. The air just cut off and the magnet. That's strange. We're okay, Jordan, don't worry. Okay. Then that's always my fire drill thing, like, okay, let's go. Let's hope we don't have a fire drill. Okay, so, oh, there's the heater. We're good. This point is on the curve, right? So it has a coordinate. Now see how x is a function of y? So now I say, okay, if y is my input, then my output is x, which is 2y cubed minus y to the 4th, right? So this coordinate point is this, yes? But also look at the blue of it. Look at the blue. If I start at the origin and I go to the right h and up r, I get to that same point. That's from h, r, don't I? So you know what h and r are. H is 2y cubed minus y to the 4th, and r is y. R is always going to be either x or y, or if you're rotating around a line that's not an axis, then you're going to have to worry about shifting by that line. If we had rotated, well, in this horizontal thing, if we had rotated around like y equals -1, then r would be y minus -1 or y plus 1, because you would think of r as the top minus bottom there. And the top is the coordinate point y. And then the bottom would have been the axis of rotation. the bottom will always be the axis of rotation, correct? Radii always go from whatever you're rotating to the axis of rotation. And so if you have an axis, a y or x-axis, then it'll be 0, minus 0. But if you have a different line, and we'll do one of those. Okay, so r is y, h is right minus left. And what is right minus left here? Yeah, 2y cubed minus y to the fourth, because I'm in the first quadrant, minus 0, because the left is the x-axis. Okay, so now I've run out of room, but my area, which is 2 pi rh, is 2 pi. R is 2y to the third minus y to the fourth, and h is y. And so now, so I'm right here. I'm going to take that down to here. So I have a little bit of volume to that paper towel roll. If I take that surface area of the paper towel roll and I multiply by the thickness of the paper towel roll, notice what kind of thickness is this? Is this a dy thickness or a dx thickness? It's a dy thickness, isn't it? So it's all working out. So then the little bit of volume based on how thick the cardboard is in the center of the paper towel is this. And then the total volume will be when I add all of that up. And for what y values should I be doing this? 0 to 2, because I look at the original blue, or in this case orange, I look at the original orange area that I rotated, and I can see that these right minus lefts need to be done starting here at y equals 0, and then ending up at y equals 2. So 0 to 2 are my bounds. And that's what we get. All right. I think on this page I have steps written down. And that's like my normal MO where I tell you what we're doing and I do an example to show you how it's done, and now I've written down exactly what we've done, or attempted to. Because a lot of this is just a lot of vision. So absolutely draw the region that you're rotating. Okay, maybe even shade this. Because that's really important. If that region is top minus bottom or right minus left, you already know what your variable of integration is. Then you're going to draw a representative cylindrical cross section. Find the height and the radius of the cylinder. The height is parallel to the axis of rotation. It's also determined by the area. If it's vertical, then you'll have x's. If it's horizontal, then you'll have y's. The radius is usually just x or y, but may involve a number also if you're rotating around a line other than an axis, which is the question Terry had that we just addressed in number 2. Write the formula for your surface area of a cylindrical shell. Plug in your r and h that you found in step 2. Find the volume by multiplying by dx or dy and add them all up with an integral. Number 2 is the hard step, right? Well, number 1 can be hard too. Right, I'm going to pause this for Jordan. Yeah. Okay, so here we have our first example. We have y equals 2x minus x squared and the x-axis in the first quadrant around the y-axis. So I know you guys, your favorite part is graphing it. So I'm going to let you muddle through this for a little bit. How am I supposed to graph this? There is a parabola. Upside down. Once you know that, just find the intercepts. The vertex is in between somewhere. Well, vertex is exactly halfway between, but then we don't know how tall. But yeah, the intercepts, x-intercepts are what? 2 and 0. upside down parabola with intercepts at 0 and 2. That's all you need to know. The x-axis. This is the x-axis. Okay, so do you see the area we're rotating? This is a lot like the example I was talking about to begin with, right? Okay, so let me shape this area. Here's the area I'm rotating. Okay, which line are we going around? The y-axis. Here is the y-axis. I'm rotating around it. And so I'm getting a bundt cake if my hole had a diameter of 0 once I rotate this, right? When you rotate this, you get the bundt cake. Okay, so look at the blue area before you look at the volume. Look at that blue area. Do we have top minus bottom or right minus left or either? Definite top minus bottom. If you look at that curve, the parabola is the top the whole way. If you think about it as being right minus left, well, it's both the right and the left, so you don't want to do that. So I have top minus bottom, and I am rotating around the y-axis. So how does the y-axis compare to this? Is the y-axis perpendicular or parallel? It's parallel. And so we're going to have a shell. So here is this blue, this dark blue cylindrical shell is my typical cross-section shell. And the area of this cylindrical shell is 2 pi r h. I have to figure out r, and I have to figure out h. Oh, what letters in the answer? X or Y? X, X, because my blue area, my turquoise area here is a top minus bottom area. And this line I drew goes from a top to a bottom. And so this is functions of X. So I need to see the letter X in my answers. Okay, so the H is always inside of the area that you rotate. It is the top minus bottom here. And so what is the top function of X? 2x minus x squared. And the bottom, 0. Right. And the radius goes from the point in the area, which is at the location of whatever this x is, so it's x. And then minus, this is an axis, so minus 0. So the radius is just x here. So I'm not going around a line other than an axis. And so now I can plug into the area of my cylindrical shell. So 2 pi x, 2x minus x squared. Notice the thickness of the toilet paper roll or the cylindrical shell is a dx thickness. So that works to making this volume, this little bit of volume is if I multiply the cross-sectional, or it's not, piece, the area by dx. And so for my total volume, I should add these all up. But for which x values should I be doing this? For which x values am I rotating these areas? 0 to 2. Done. What's the hardest part? Oh, solving the integral. A lot of times in the volume ones, you don't have to solve the integral. The integral is the answer. So what's the other hardest part? Determining which variable to use. Okay. So how do you determine which variable to use? Okay. What's top minus bottom? the original area you're rotating. Yep, you're right. That's exactly what. So this turquoise told me that I'm doing dx's because it had to be top minus bottom. Okay. Good. Now, in this example, we're going to do two questions. This is going to be an area that's not necessarily top minus bottom or right minus left, but I want you to do shells. So you'll have to know whether to do top minus bottom or right minus left if doing shells. Okay. We're going to be in the first quadrant. You know that much. What's the graph of x equals y squared? Yeah, it's a parabola opening to the right, and since I'm in the first quadrant only, I really only have to worry about that. Because that's y equals radical x. Yep. Also, so this is the graph of y equals radical x as a function of x, right? Or as a function of y, this is x equals y squared. Because my function is monotonically increasing, so it passes a vertical line test and a horizontal line test. So you could think of it as a function of x or as a function of y. Okay, and you're going to have to, in this particular example, I'm going to make you think of it as both one at a time, but yeah. Okay, what about x equals y cubed? Or sorry, y equals x cubed? It's this, right? Now how does that fit over here? If we're not sure, okay, so y equals x cubed and y squared equals x. We want to find the intersection of these, okay? So let's take it, y equals x cubed, and let's put it in here. So instead of y squared, I have x cubed squared equals x. So x to the 6th equals x. This only happens for two x values, 0 and 1. Also, if you weren't sure about that, 0 equals x minus x to the 6th. Factor out an x. This only has two solutions, x equals 0 and x to the 5th equals 1, which is x equals 1. So 0 and 1, those are my intersections. So 0, 0, and 1. What is y going to be when x is 1? 1. And so do I go underneath or over? You can just test, like, what if x is a half? It will go underneath, though. Okay, so I have to pretty much zoom in on this very narrow spot. I'm going to do that in the next one. So this was y equals x cubed. Also, x equals cube root of y. Because I could think of it as a function of x or y. And then here, here is y equals radical x, or x equals y squared. And so these intersect at 0, 0, and 1, 1. So, I don't know what you want to see, Terry. I just zoomed in. You can make it, it depends on which way you cross it, or you cut it. So notice, is this top minus bottom or right minus left, or either one? Either one, right? Either one. Okay, so in question A, which axis am I going around? Y. So let's go around the y-axis here. Now, if you have to use shells, and you're going around this y-axis, which is a vertical line, I need to use a vertical line, right? Because I need them both to be parallel to make a shell. You want to do this. And then when it rotates, it makes a shell. Do you see that? Okay, so what letter is that? X, because the line I drew here was a top minus bottom. So for A, I'm going to do A in blue. Here is the height of my cylinder, and here's the radius.
So can you concern like a right minus left and the y-axis of the wash?
Yes. If I were to go around the y-axis and I did a right minus left, I would get a washer. And I would use a totally different area formula because I have a washer. Okay, but I'm doing a shell because we're practicing shells. Later on, we'll practice all of them. So here, what is the height? The height is the top minus bottom. And so the top function as a function of x is square root of x, and the bottom function as a function of x is x to the third. And the radius is right minus left, and it's just x here, because the left is the axis, the y-axis. And so the surface area of my cylindrical shell is 2 pi RH. And so if I multiply that by dx, I get volume. Oh, we're out of time. Okay, so we can finish these next time.